other people come in, then they'll come in. I don't think this clustering one is going to be super duper long. We just have a lot of demos because it's very much a more visual topic. I will do lots of drawing on the board as well. So last week we talked about like types of ensembling and like a little bit of clustering. I sort of give you guys like an overview of like the notes I used to create the slideshows basically. But yeah, for ensembling we talked about boosting, bagging, all of that stuff. This is like taking a step in a different direction. So this is sort of we're going more into the weeds of unsupervised learning. I think next week we're doing dimensionality reduction. I think I won't be the one teaching that, someone else is, but this is sort of like the first look at unsupervised learning. So we can talk a little bit about that first. We're going to talk about clustering and whatnot. We're going to be going over the intro to clustering and then three main types of clustering: K-means, Gaussian mixture models, and then agglomerative clustering. We're going to talk about the EM algorithm, which is sort of like what the GMMs use for clustering. We're not going to get super mathy into it. I just want you guys to understand the concepts this time. The math stuff is more you'll learn than your upper divisions. This is sort of like an intro to what it is. So this is like, clustering is the first look we're going to do at unsupervised learning. So far up to this point, everything we've done, supervised learning, we're looking at patterns, we're training models, trying to predict something. We did that with decision trees, we did that with neural networks, we did that with linear classifiers. That's everything that we've been doing up to this point. So now like in your mind, if you think of machine learning, you're going to think of, I have a question and I want this math computery thing to answer that. That's essentially what supervised learning is. Now when you think about unsupervised learning, what do you think of? If you answer, I'll give you guys, I'll throw a chocolate to you. Chocolates.
I know it uses like a more specific training data. That's what I think.
Like unsupervised, there's more specific training data. Okay. I'm gonna try to throw. I'm not the best thrower, but I will try.
I suck at catching. Yeah,
Oh,
there you go.
Okay.
It's all good.
It's all right. If not, I'll like partition out chocolates because there's only like 4 of you guys. Well, I guess Julian is one too. 5 of you guys anyway. I'll just make piles and just distribute them at the end. Or you can just take one if you want. Like honestly, there's a bunch. Yeah, more specific data set. That's one way to think about it. Applies to supervised learning too. What else do you think of? Listen, when you think of just the word unsupervised.
Like unsupervised, like you do not tell the pattern, but like for supervised, it's like you already give it a pattern and then
Yeah, sort of.
You're just like you're not really watching it, you're just letting it run, whatever like algorithm you like program it or
Exactly. So all 3 of you guys are all saying the right things. It's sort of just letting it do its thing, right? You're not saying what's right or wrong. That's not your point. You're not trying to test it anyway. Your whole point is that you have some data set. You want to find some patterns. You want to know what's going on here. There's a couple of types of it. Looking for patterns, explaining data, looking for missing data, and feature selection. These are the main points of unsupervised learning. What you're not trying to do is answer, like for example, with decision trees, what happens if I do X? What will happen? That's not what you're trying to do. You're given a bunch of data, you just want to understand something from it, and the task that the model is given is finding that thing. So clustering, just like by yourself, you think of clustering, you're going to think of like groups of things, putting stuff together. That's exactly right. Clustering just describes data by discrete groups with some characteristics. One of the ways that I always think of clustering that helps me is just think of them as like those little groups of balloons. That's basically what it is. You are taking this data, which could be the balloons, and tying them together and making this little group of them. That's what clustering is. Does that make sense to everyone?
Yeah.
Okay. So now we're going to look at types of clustering. So this is sort of applies just generally. These are not algorithms of clustering. This is just if you look at your data, nothing on it, you just want to see what the points look like. There are 3 main ways to look at it. You might think first, there's one called location. So when you think of location in this example, where would you put the points? Like how would you draw out the clusters? You have these points and these points. If it's location based, where would you draw them out? You guys can just yell out loud. No one needs to raise hands because there's not that many of us anyway. I'll build the first one. This could be a cluster.
Maybe that one right there. Top
Yeah.
left.
And this would be another cluster. And this is location based because we're making these clusters based on where the points are on the graph. The other one is sort of like shape based. So how would you guys draw it here?
If you maybe look at the third one right there, like, well, not third one, but I'm talking about like the one with, I think that's 10, wait, no, 9. No, it's like at the right side. I'm
On the
pretty
right
sure.
side here.
Yeah, a little bit more. Yeah, like that little group right there.
Oh yeah, that's yeah. I feel
Yeah.
like I could do that. I was like, I feel like it's just easier. Okay, this would be density based. I feel like I should have made borders between these.
Yeah.
These are the graphs. This is more density based because this is like super dense, they're super close together. So the second one is would be like this. What about shape based? This one's more interesting. Someone want to come up and draw the shape
Top and
based
the
one?
bottom.
Yeah, exactly. Yes, the top and the bottom. There's a big crescent shaped thing over here.
It looks like a palm tree.
Like what?
I'm thinking of like a little sea anemone from like SpongeBob SquarePants, you know what I'm saying?
It kind of looks like it's like eating the top one's eating the bottom one, the shape one.
Little amoeba.
Yeah, it's eating like an amoeba. Yeah. Yeah, that's types of clustering. Do we have a duster? Oh, that's not a duster.
I think there's one in the drawer on the left side.
Oh, here, right? Oh, yeah, there it is. Yeah, these are just the types of clustering. So this is just saying that, like, if you want to, okay, the main thing is that we're gonna look at 3 different types of clustering algorithms, right? Just the same way that when you get your data and you need to choose what model to do for supervised learning, you have to do the same thing for unsupervised. And bunch of types of data, you have to decide which type of model am I going to select for supervised. Same thing goes in unsupervised. The first thing you will always do is look at your data visually first. Then you're going to decide, how much data do I have? How does it look like? And based on that, you can decide what exactly you're going to do. Okay, now let me erase this before I go on to the next one. Then we're going to be drawing more stuff. So first, we're going to look at an example. And this might be weird, we're looking at examples of it, but I think this is a very intuitive example. This is clustering and data compression. So when I say data compression, what I'm talking about is that when you have like a nice looking image like this, and you go ahead and you just pixelate it. So intuitively speaking, how do you think that this would happen? You need to think about clustering right now, but how do I know what color to make each pixel? How do I like put the pixels together and decide what color to make it so I can pixelate it? Yeah.
Classify each cluster or bigger pixel by what color has the most smaller pixels inside of it.
Yeah, you can be like, okay, I'm gonna look at this pixel here. Let's put whatever's together here and move on. Here's the chocolate. And this is literally just you have to make each square a center of some region and then average out the pixels there and be like, yeah, that's gonna be my new color. That's exactly what we do. We convert the image into RGB in case it isn't, flatten it to being 2D because we have to do distances, and then we apply a clustering algorithm and replace each pixel with the mean value. And if you look here at the paired picture, you can tell it is the mean value. Is the average value between those pixels that are there. That's the general idea. That's how I want you guys to think about how clustering works. It's not just some like spooky thing. It has actual applications too. And so the first one I'm going to talk about is k-means clustering. This is the simplest clustering algorithm. If I asked you to make up a clustering algorithm, you'd probably think about something like this. The main idea is that you have all these points and you want to put them into clusters, and the way you're going to do that is by first assigning them based on which one is closest to the middle of the cluster. Do you guys remember when we talked about the centroid model? It was like the very first or second lecture from fall quarter. We basically just went over a type of model that you have a bunch of data, and you know the classes, and in all those classes, you take the average of the features and you call that the middle, and when you get a new value, you see how close it is to each one of the clusters as middles, and you say, all right, that's how I predict it. It's very similar to this, where if I knew all of these were class A, all of these were class B, this was class, this was class C, this was my middle, and I got a new data point, this is for supervised learning, and it was like over here, that's close to that, so I'm gonna assume this is a type of point. And that's sort of like a supervised learning version of it, as like a review, that's what we did last quarter. The main thing is that like how clustering works is just two steps. Put the data to the closest middle of the cluster, and then take the average of all the clusters features with XY points now, and then make a new middle. And this is going to be very apparent with this example here. Now 6 points. We'll do like 7 clusters. Okay, these are our points. You see how the middle is moving? So look. Oh, these colors kind of weird. These here are our points. The big one is the middle. And watch what happens at each iteration. So let's go back. This is original. When we just have some random clusters, we've assigned them in some way, this is how they're going to look like. We do one iteration. We take all the points that are currently in here, regardless of what their original cluster assignment is, see how close are they to the other clusters of middles, and then reassign them. And then based on this new assignment, we take the average and make a new middle. And see as you go on, well now it converged, but it scooches along. See how they get closer and closer to their actual points, and now it's done. Does that make sense to everyone how this sort of works? Raise your hand if you have questions on how this works. Yes.
Can you do the explanation you did like just 30 seconds ago again?
Yeah. So what it's doing is that you have randomly assigned cluster middles. These are not good cluster middles, they're just randomly there. And what we're gonna do is that we're gonna go through every single point and find which cluster middle, the big circle, is closest to it. So for example, if I went with this point, the one closest to it is this one right here. And so I'm gonna say, okay, this belongs to this cluster now. So all the purple ones have the closest distance to that big purple circle. And so now you're like, okay, now I know that what's closest to the random one. But look at it, look at that purple circle. Does that purple circle looks like it's in the middle of all the purple dots? It's not, right? It's way off to the side. That's weird. That's not the center at all. So what it's gonna do is it's going to take the average of all those points and it's gonna find what the middle one is. You'll see that. If you click play. Look, now it's in the middle. It's in the middle of all the purple dots. And so now we have a new middle. So now we're going to redo the previous step. We're going to go through all the points, find out what is closest to each cluster's middle, and reassign them again. And then we're going to recompute the middle again. And watch it again. Assignment slightly changed, the center slightly changed. We're going to do it again. Slightly changed. But notice each step of the way, it's moving only a little bit and a little bit every single time. Because every single time we're getting closer and closer to converging. We're getting closer to having the correct assignments, that each one of the points that are closer together are in the correct location. It's only moving a little bit. And now it's done. Does that make sense?
Yeah.
Yeah. Okay. That's basically how this system works. And so the notation we typically use is we call mu, that's going to be our center because that's the mean of all of the feature values. The way that I would think about it is like, this is like x, y, x and y, this is x, this is y. And you literally just take the average of the x coordinates and the y coordinates and you find the mean. That's how we're going to find the middle. And each step of the way you assign the points to the new closest cluster. We're gonna do this together visually. You don't have to calculate the distance because you can there's a graph lining in the background of this. It's just not very dark. So we're gonna try to split this into 2 different clusters. I'm gonna move this down because I'm not tall enough to reach that. Sorry. I was like, let's squish that down a bit. There. Better. Okay. So our randomly assigned clusters are these 2 points. So we have a purple one and a pink one. So our k is equal to 2. These 2 here. And we're just gonna guess and see which cluster it's gonna belong to. This is our first iteration. And these are our 2 mu's. This is our mu1. This is gonna be our mu2. So let's start on this side. Which cluster is this one closest to? Pink or
U2.
purple? 2. So it's gonna go here. How about this one?
That's U2.
What about this one?
U1.
Guys, you guys all need to say it. How about this one?
U1.
You won.
New one. All right, now let's guess. If we have this as our cluster, this is our cluster, what will be the center of this one approximately? Like, just guess. What is the middle of these 3 points? What will our new mu be?
So confused.
So remember, the first step that we do is that we go through, look at the points, assign them to a randomly assigned mu. And then we look at it and we're like, okay, this is gonna be cluster 1, this is gonna be cluster 2. But the point of the mu is it's the average of the points. The point is it has to be in the center of the cluster. Right now, our center is here. Is that the center? No. So we need to find the center of the cluster. That will be our new mu. So for this one here, this is where our current center is. Where should the center be?
I'd rather.
Does someone want to come up and then like mark it on the next graph? Who wants to come up?
Sure, I'll do it.
All right. Where will the new centers be?
You said it'd be.
Yeah.
Probably like right here.
Yeah.
Yeah.
And how about in the second one?
Second one. I guess you can just put it like right here. Pretty
Yeah,
sure.
pretty much, yeah.
Oh, okay.
Yeah, that's right. That's where we'd be. This is the center, that's the center.
Oh, okay.
And so now, when we had the purple and the pink before, now we've moved them. I remember in the first example where we had those purple clusters, and the first one, it was like way off to the side. We moved it and it was smack dab in the middle. We're doing the same thing again now. So now that we have our new assignments, we repeat the same step as before. And what was the first step of the algorithm? Assign the data to whichever middle is closest to it. Now, this is gonna be our mu1, this is gonna be our mu2. Now that this is our new middle, this is our other new middle, we're gonna go through all the points and assign them again. What's close? Is this closer to this middle or this middle?
Middle one.
Middle one. How about this one?
Also middle one.
How about this one?
And one.
One.
This one?
Two. Two.
Okay, does that make sense? How the k-means clustering algorithm works?
A little
Yes.
bit.
A little bit? Yeah, that's like the step by step. It's always the same thing. And then once you get the same result twice, you're like, all right, this is done. We found our new middle. This was the same result as in the previous iteration when we just newly assigned it. So now we just double checked it. And it's the same thing. So we know this is the correct clusters. Does that make sense?
Yeah.
A little bit?
So like, what's the function of like the third iteration for the, if only 2 iterations can get?
I mean, let's say that the original points that we had were way off. Like, let's say that our original clusters, or we had more points here in the middle, and we had like, let's say we had one over here, another one like over here, and let's say this one is actually closer to this one, but it's been assigned to this one because the middle is like somewhere over here. I think the main thing is that like you might have more iterations than 2 if you have points that are outliers. Because think about it. If I had a point, we can do this again. Let me just erase. Let's add some more points. Oh, weird. Hmm. Okay, let's say we had this graph now. In our first iteration, if we have this, we'll have these be the same. And this will probably be over here. This will be the same. I think this is closer to this one. But when we do the middle of all of these, it might be more off. Or let's say we had another point that was sort of in the middle of all of this one. That like happened to be assigned to the wrong cluster. Then you would need more iterations to fix that. In other words, the more iterations, the more data points you have, and the more mixed in they have, the more outliers you have, the more likely it is that you're going to get clusters that aren't exact in the middle, because the outlier will always pull it out. And that will cause like points over here to get misclassified. Like let's say we had another one over here. And now our center is say over here. And this one's center is now going to be over here. Then some points that belong in a different cluster might get misclassified. And it might take more time for it to be in the correct middle.
I need to have like more iterations.
Yeah, you need to
after-
have more iterations,
okay.
basically. It'll happen when you have a larger data set. It might take more time. Okay, does that make sense? Okay.
So for that one, when there's I know for a lot of training things, you can't use all your data for everything because calculating all those distances messes things up. So when you're using a random sample of the data, like do you use the same random sample for all of the k-means clustering and then compare the mu's afterwards? Or because if you use random things each time, I could see like the mu's always moving because there's a different set of points every
I see
time.
what you're saying.
Which approach is the one?
So the approach that we'll take for initializing is that you'll start off the very first clusters that you choose will be random, because regardless of what you assign to them, they could be already existing points in your data set. They could be points that aren't in your data set. It's just a mu. It's a random value of mu. So the first value you choose will always be random. It could also be distance based, but let's say it's random. But every other value of mu after that will always be the average. And let's say that for our example here again, that our original values weren't these purple and pink ones. We started off with something like one of the mu's was like over here, and the other one was over here. Eventually, they will get fixated to here and here. Because what we'll do is that we'll say, if we have this as our mu, and this is our mu. Let's take this step by step. So these are quite far, this is quite far from where it's supposed to be. And so as we go through this step, our first center will be here. Then will be the other one. This is fairly close to this. This is just gonna, this is more like closer to the other one. This is gonna be here, this is gonna be here.
So the purple X will be just the outline. Oh, wait, never mind.
No, the purple one will be part of that one too, because that's what's closest to. The average of this cluster here will probably be somewhere over here.
Is there no like specific range for like the amount of iterations of like how far like or what's close?
Like, what do you mean?
Like you know how you said the purple X belongs to like to the mu one, right? Yeah, like is there like any like range of how far it's supposed to be?
There can be, but the main thing like k-means clustering is that you must have k clusters. So if I only have 2 clusters, then even the weird point over in the corner has to belong to one of the 2 clusters. Let's say I had k equals 3 and one of my mu's, and this was like a way out there outlier. It could be that I could have a cluster that's just this point alone. That's possible. In fact, if I had, see how many points are on here? 6. If I had k equals 6, each point would be its own cluster. So it really depends on how many k's you have, because as you increase it gets more complex, and you can account for things like this outlier being in its own cluster. But going back to your question, the first one you assign is always random. But regardless, if your random is such a bad estimate. It's just way out there random. It'll take more iterations, but eventually, you can see here, it'll get closer and closer to the actual point it's supposed to be. Yeah.
No, what I meant was like, because I know for large data sets, running all those distance calculations is there's a word for what I'm trying to say, but I don't remember what the word was because it was a month or two ago. But it's like when you do the training, you batch train, or like you train on randomly selected of the data set.
Yeah.
But because it would you take that one batch and then find the absolute mu when it's no longer moving at all, and then compare them? Or would you find a new batch every time and keep the same mu? Because I'm assuming then the mu could infinitely move because it's a different center every time.
I see what you're saying. So in the case that we had, let's say we did like a batch version of this thing, or each time we just have like 2 points at once. You would run each batch till the mu is no longer moving. And then after that, it's up to your discretion. What you could do is that for each one of the batches, you could say, okay, find the mu till it's done. And in each single iteration, you randomly choose the first initial mean. So you keep restarting every single time. Or you could do the other way where in each one of the batches, whatever the previous batch's last mu was, you could continue holding that too. So it depends, it's up to you. But regardless, at the last batch, you will have a final mu value.
Yeah.
Yes, okay. So initializing clusters. The way that is the most easiest to do is just to do it randomly. Choose one random data point or choose just any random value on your graph and choose that to be your mu. Typically, you want to choose a random data index. Like, why would you want to choose a data index versus just a random data point on your graph? And what are the pros and cons of it? Choosing just a random value on the graph versus a data point.
Just inaccuracies.
Yeah, if you choose a random point on your graph, it is possible that you just get like cluster values that are just way off, that are nowhere even near your clusters. Versus if you choose a random data index, at least that point is guaranteed to be in the cluster and is more likely to accurately represent whatever your future mean will be. It ensures centers are near some data. The other one is also do a distance based. Start with one random point and then find the point farthest from the clusters chosen so far. The thing about this way is that you may choose an outlier in this matter. Random is probably the easiest way to do it. Now we're thinking, how do we choose the value of k? If I have my 6 data points, how do I know how many clusters I should make of this that are more accurate to showing what's here? You might look at this picture over here and think we should do maybe k equals 4. Each one of those data points in like the upper left-hand corner there should be their own cluster because they're so far apart. And maybe the ones in the bottom right corner should be one cluster together. But you don't know how, what should I do? The important thing to know here is that the more values of k that you have, the more complex your model becomes. As k increases, so does your model's complexity. So if you guys remember, do you remember things like, I don't know if they went over this last quarter, but like things like ridge regression and lasso regression. The idea of penalizing your model if its parameters get too big to avoid overfitting it. And the way to think about this is that if I have a bunch of points, let's say this is my graph and I want to run a best fit line through it. If I make a super duper, let's move this graph down so I can write on the board. Oops. Like, let's say I have this as my graph. And what I want to do is I want to find the best fit line. If I overfit my model, I could get something like this that goes like this. And that's like 100% training accuracy. I'm hitting every single point at every single value. But the moment I introduce the test data, it's not gonna do good because this is overfitting it. And so a way to account for this is to penalize having big parameters, because a very complex math model like this is gonna have very big coefficients. So if we just want maybe just like a straight line of some kind, like we just want this, then what you want to do is you want to penalize for having too big of parameters. And you can do a similar thing with k-means clustering. You can go through all of your values of k, and to ensure that the values don't get too big, you can say, hey, if I have values of k that are accurately showing up on, that are accurately like making clusters of my data, but the k value is too big, say for like 100 one, that k equals 100, you can penalize it saying, no, too big of values of k is bad. Does k-means clustering make sense?
Yeah.
Yeah, okay. The next idea, it sounds scary, it's the Gaussian mixture models.
Yes.
So do you guys remember what Gaussian means?
Was this like Falkware?
No, this is just general. I've like it's like I think this was in stats.
Yeah, it's stats.
Like a normal distribution?
Yeah, it's just a normal distribution. It's just fancy when I say normal distribution. And that's all it is. It's just the bell curves here. That's all it means. The main idea of the Gaussian mixture model that's better than this is called a generative model. And that is because it'll give a probability for each one of the data points. Rather than in k-means, what we did is that we took every point and we said, yeah, you belong to cluster 1, you belong to cluster 2. In the Gaussian mixture model, you don't do that. You give a probability of how likely the point is to belong to clusters 1, 2, and 3, for example. These clusters are not modeled just as means, but you guys raise your hand if you know normal distributions. You learned about normal distributions. You guys remember, okay. If I said make a normal distribution for the data, how would you, like, I tell you it's normal, you have to model it. What are the two values of normal distributions that you like play around and tweak with? Typically.
You just categorize them?
Yeah, like you categorize them. But like if I asked you to make a if I asked you to make a Gaussian model of some data, the two things that you play around with is the mean and the variance. That's how you change how tall and how wide the cluster, how tall and wide the bell curve is. Do you guys remember that? Is that like, you guys trying to remember about stats, how they did that? It's like I think like there was like that big equation that was like z equals like 1 over, there's like a pi in there for some reason, and it was all squared and all that. But the values that you tweaked were mean and the variance. Each cluster is a bell curve, and each data point is going to be a mixture of them. And that's sort of what this picture here is saying. I like this picture, where you can see each one of the values of the mean and the variance, each one of these curves. And you see the data points here, they're given a certain probability of how likely they are to belong in each one of these clusters. Like the ones along these edges, like over here, you can see it's below the red one, but it's assigned as green because the value of the green here, the probability of the green is higher than the probability of the red. Does the concept of a Gaussian mixture model sound like, is that like making sense? Like just the concept of it? Here's any have questions on the concept of it. Yes.
Can you just explain again, right now what you said, like the graph is green, even though it's like below the red one?
Yeah. So each point is assigned a probability of it being in the red, the green, and the blue. And you can see that each one of these is under a bell curve or bell curves in some cases. For example, this red one here is right at the mean. So you know for sure that the probability it's in the red cluster is 100%. It's close to 0 for the green, close and definitely 0 for the blue. As you go here, you see that there's overlap between the two clusters. So how do you know which one to choose? Each one of these points is assigned a probability, which, let's say I draw a line from this point onward. Where given sort of like the characteristics of this data point, you can get the probability, because raise your hand, you guys remember the probability distribution, PDF and stuff like that in stats. A little bit. each distribution is a PDF. Each cluster is a bell curve. Each bell curve therefore has a PDF. Think of the PDF, just ring a bell. You give it the X and it tells you the probability, which quartile it's in basically. You know, is it right there is it by the mean? Where is it what's the probability that this is gonna happen? That's basically what it's gonna say. That's how we're gonna think of it. That's what this graph is saying. If I get to this point here, I'm gonna look at how likely it is to be in the green, how likely it is to be in the red. The probability the green is greater than the red, so I assign it that way. And we know this because we can find out the probability distribution of each cluster. So in a k-means cluster, the probability distribution is basically just uniform. Because each point is 100% in this cluster and 0% and 0% in the other cluster. In this one, you can have, it depends. It can be like 70-30, it could be 50-60, it can be anything. Does that make sense? More sense? Okay. So like I said before, the Gaussian is defined by the mean and the variance. The variance is how spread out the data is. That sort of determines like how wide is this cluster. A cluster with a lot of variance, it will encompass a lot of the data. And then the mean is sort of like how skinny it is. And these are like the two values that you use to define any normal distribution and how we're going to define the clusters as well. We're wondering, why do we do a mixture? Why can't we just have, like in this case, why can't we just have like one mega cluster that just goes across absolutely everything and covers every single point? Why shouldn't we do that? Why should we have multiple clusters? If you have multiple clusters, yeah.
Do we need to classify them as multiple different types of things, or probabilities of different types of things?
Yeah, it'll be more accurate. If you just have one mega cluster, like that's not gonna accurately represent what our data is showing. That's like if I went to k-means here, and I just said, I'm gonna put everything in one big circle. Yeah, it's in a cluster, but it's not gonna accurately show our data. And it's the same thing here. One bell curve for each cluster, and then each Gaussian also has a weight on how likely it is that a random point comes from that cluster. You will definitely have, and you can see that here too. The green cluster is a lot bigger. It has, or yeah, which one's the biggest one? The blue one is the widest cluster, has the most variance, it has the greatest spread. It covers the most data points out of everything. If I gave you a random point, it's more likely to come from that blue cluster because it's encompassing more of the data.
I'll go for like the red one.
The
Usually.
red, yeah, same thing with the red one. Like the green one is the one that has the least amount of variance in it. The blue one's like from here to here. Red one's like from here to here. Maybe it's from here to here. But yeah, so it's like that's why we use a mixture. The mixture is the same thing in like k-means. We have multiple k's. It's the same idea with the Gaussian. You have multiple clusters, multiple Gaussians. So instead of assigning each point to a cluster like k-means, it's going to assign a probability to each point. So go on to the idea of the EM. So the way that it like decides what this probability is going to be is called this algorithm called the expectation maximization algorithm. Okay, raise your hand if you remember what expectation means in stats. What's that another word for? If I tell you the expectation of this data.
It's like how likely or how often you expect to see something.
Kind of, yeah, it's the mean. Expectation is just a fancy way to say the mean. So in this case, we're just maximizing the mean. And that's kind of what we do with k-means. We're trying to find the best mean to show that to represent that cluster. So the first step is the expectation, which is to estimate the probability it belongs in each Gaussian. And that makes sense. Like we are expecting how likely it is to be in here. It's sort of like the calculating the likelihood. And thing. Who has taken like any of like the upper division stats classes? No, okay, do you guys remember Bayes' theorem? Okay, okay. There's the idea of stats, right? You have the probability that A is gonna happen given something in B, right? Do you guys remember it was like the notation that goes like this? D of A given B. It's like the probability I'm gonna drink coffee given I'm already in Starbucks. That's a lot higher versus if I said probably I'm gonna drink coffee while I'm in the middle of the ocean. It's the probability something's gonna happen depending on something else. That's what the E step does. The probability that this data is here, the probability that that this data is in cluster A, no, actually the probability is cluster A is the given. That is the given. You're just trying to figure out where it belongs, and we need to find the probability that it's in that one by assuming it's already there. So after we get this probability, it's the answer maximization step. This is very similar to what we did in k-means. Remember in k-means, our center was just the average of everything that was in that cluster at that time. That we had these 3 points right there, and we said, yeah, the middle is in the center of them after we decided how close they were to the purple and the pink. It's the same thing here, except instead of updating just the x and y coordinate like we did in k-means, we update its mean, variance, and weight based on the probabilities that the data points belong in those clusters. And so we keep doing this. So it's the same thing as k-means, but rather than just directly saying you belong to this cluster because you're closest to it, we have a probability that it belongs to that cluster based on its like properties. Does that make sense? Raise your hand if you have questions. Good? Here's gonna be an example. I feel like hopefully this will make more sense. Imagine you have a bunch of heights of people in elementary school and junior high and in high school. So you have a wide distribution of these heights. Now the heights can overlap. Let's say you're like the 12-year-old in elementary school. You're right about to go to middle school. You might be a lot taller than elementary school kids and closer to the height of the middle school kids, but technically you're in elementary school. So they're gonna overlap at like the end point, at the end of elementary, the beginning of junior high, end of junior high, beginning of high school, they're gonna overlap. But you know that each group follows a bell curve. So this is, could say that, let's say for, if this is height, we'll say it goes from like, how tall is a kid? Like 3 feet? Up to like 6 feet. I feel like 3 feet's wrong. I don't think kids are 3 feet. Maybe like, I'll say 4 instead. That makes more sense. Okay. 5 feet here. We'll say that in elementary school, we'll say most kids are like around 4 feet, but you have like a wide variety of them. Maybe they're like sort of like this. And then we'll say maybe for junior high, you have a lot of kids at around 5 feet. Maybe some of them are getting there. And maybe we'll say high school, you know, it's like this. It's like that. There is overlap over here and over here between the beginning and ends of them. And so you could think of this idea as a Gaussian mixture model because we have these different heights of elementary, junior high, and high school. And each group, you don't know who belongs in which group. If I gave you the height of a kid being 4 feet tall, you'd be like, yeah, most likely in elementary school. Versus if I said something like 5'7", you would be like, you know, maybe 6 feet. You'd say like, oh, maybe they're over here. There's like an overlap here. See, it's at the end of junior high, and it's at the junior high mixture model, and it's inside of the high school mixture model. But the probability of being in high school and being 5'7" is a lot greater than being in junior high and being 5'7". Does GMMs make more sense now?
So it's just kind of like a Venn diagram a little bit.
Yeah, basically, it's like a Venn diagram.
Okay.
That's the general idea of it. Okay. So wait, so now does like GMMs and EM algorithm make more sense? Okay. We're gonna go into agglomerative clustering. This one's a lot less scary than it sounds. And this is the idea of agglomerative. Raise your hand if you've seen like those evolution diagrams where it's like you start off as like that weird alligator thing, and then as time goes on, it becomes something else. It's evolutionary. You guys have seen those, right? In school, the evolutionary models. But you can like go and like cut it at a specific time point at when like two different species that are two different have merged into one thing. Like you could say like the dinosaurs became chickens, and there's a point in time where the dinosaurs have like merged with another species, and now they're the birds. That's the idea of what dendrogram is, and it's a visualizer for agglomerative clustering. So with agglomerative clustering, each point starts as its own cluster, and you repeatedly merge based on whatever is closest, and that's how you create your clusters. Notice here, there is no set number of clusters. There could be as many clusters as you need there to be. So the way to think about this is orientation. Everyone is like doing their own thing, and no one's really talking to each other. And then two people start talking to each other, and another person joins their group,
And it just expands on it.
and it just expands on. Maybe there's like another two separate people over there that are talking with each other, and no one joins their group. They're just talking by themselves. Maybe there's someone on their phone in the back and just is not talking to anyone, so no one goes and talks with them. That's the idea of agglomerative clustering. You merge whatever's closest, and if there's nothing close, you call it quits.
There's no limit to it, right?
There is no limit to it. And that's why as time goes on, you will have one mega cluster. Eventually you'll have one mega cluster. It is up to you to choose which point you want to splice at and say, yes, that's the point where the clusters make the most sense to me. And that's what the dendrogram does. As clusters merge, we draw like a diagram to show it. So you can see that at the end here, it all becomes one big cluster. But you start merging by a double. So you're saying that maybe at this step over here, you can cut the tree and say, okay, P and Q are a cluster, and RSTU are a cluster. Or you can cut over here and say PQ is a cluster, R is alone, and ST and U are clusters. You start off with everything being alone. These are the leaves, and the branches are all the merges. The height is how far apart clusters are when they're merged. Basically, what that's saying is that the longer the height is, that is basically saying the more time, the less likely it is that these and whatever it just got merged with are supposed to be together.
Wait, can you explain more about like the left side portion? While like the right side portion, right? It has like different like stacks to it. While the dendrogram is the left side of it is just like a one straight line, and then just goes down until it's like P and Q. Like, does it usually happen? Does it usually look like this?
It depends on our data, and like there's a good visualizer for this that we'll look at. But it entirely depends on how your data is. Let's say instead of P and Q, it's like A and B over there. I feel like then that's discrepancy makes sense. I have A and B here. And of course, A and B go together. They're the closest that they are in the alphabet. These are gonna be merged together. T and U are right next to each other in the alphabet, so they merge together. S is close to T, we're gonna merge these together. R is close to S, we're gonna merge these together. As we do in each one of the steps. If something has a very large distance between its merge and then the whatever that next merge is, it's likely that they're not close together at all. And if we had A and B here, it makes sense. B and R are not close together in the alphabet. But eventually, if there's nothing else to merge, you'll merge them. This is sort of up to you to choose how you want your clusters to look like, because at some point everything will be together. Okay, any questions on this? The dendrograms? How do we define what closeness means? See, in this example, we said it's by distance. How close is it to the other letters in the alphabet? Well, there's four main types for agglomerative clustering. There's single, complete, average, and wards. Single makes the most sense. You put whatever is closest to them together. Complete is the farthest 2 points of the clusters. So the way to think about this visually is that if you have two clusters, you'll have one point that's way up in the corner. Let's say I think I have a blank site for this. Let's say I have like a graphic.
That's how you train it. But you won't know where to play. There's not spikes. Rather, you just
This is one cluster right now. This is what's on this cluster. So if I wanted to see if what's closer, is this closer to this or this closer to this? If I did single linkage, it would be between this point and this point. 'Cause these are closest in between this one and this one. Right, because these are the closest points in the respective clusters. Versus in the farthest point linkage, it would be between this point and this point. And this one and this one. That would be complete linkage. Does that make sense? There's also average linkage, and average linkage is kind of like k-means. So with average linkage in this example, it would be between the centers of these clusters. So this would be this one over here, the average, and then we say, okay, it would be between these two. The last one is, oops, wards, which is, so already looking at this, if two points are super close together, that means they have a very low variance. There's not that much spread within the data. The points that are very much far apart have a lot of spread. If you make a cluster, do you want that cluster to have high or low variance? If you have high variance, that means the points are very spread apart.
Oh wait, no, they're low.
Yeah, you want low variance.
I was gonna say, like, depends on what the cluster's average already is. If it already is a fairly high average variance, then you would wanna kind of stay in that.
That's true, that's true. But yeah, it depends on, it's a combination of different things. But if I was like if I want to have like a very naive idea of it, I would say I don't want a lot of spread in my clusters, because I want the points to be similar in my clusters. So the idea of wards linkage is that you want to merge together clusters or points that you know are not going to increase the variance by a lot. You want to keep it low. Now we're gonna look at this really cool clustering website. We have a bunch of different types of algorithms. We're gonna look at k-means first. You can see the type of data you want, and this is sort of like, remember I was saying like shape. A lot of different ways you can do it. It's cool. We're going to do Gaussian blobs. We're gonna do like 20 points. We'll do 3 clusters. Generate, and then let's run it. That was way too fast. We'll stop. So this is for k-means. We start off with these random points over here to be our centers. I'm gonna go ahead and move a step forward. Now we're checking the distance between for this cluster. Keep doing that, and now we've decided this one's gonna be blue. Check the distance. What's closest? The blue. We're gonna keep doing that. So all of these ones are closest to the blue, and we're gonna keep doing that. Okay. So if you look at this image, this is gonna be an interesting idea. It's like, look, everything is similar to the blue. Nothing changed the green. Nothing was close to the green. And these were close to the red. The green stayed as it was. This is going to take a couple of iterations because the way that we started off with the random clusters was not good. They were all just in the corner. Now we're going to go again. I'll just run it completely. I'm going to keep going. And the clusters are done. But notice here, look. Nothing happened to cluster 2. Everything is either blue or red. With k-means, sometimes this will happen. Sometimes you will end up having like one cluster that will either make it too overfitted and make it so that your random value is like splitting up something too much than you want it to, or it won't split at all. This will be interesting. It's like a mini batch k idea. But that's I want to add agglomerative on there. I guess I was wrong. But that's the idea of clustering there with k-means. Does that make sense? Okay. Now let's talk about when we use each. So if you have a really small data set, you can use agglomerative. But anyway, why would you not want to use agglomerative when you have a big data set? When we looked at agglomerative, we saw that it started off looking at each one of the points, looking at how close each one of them, because we started with all of them having individual clusters. Then we started looking at how close they all are if you use single linkage. And then we merge them together and slowly. And the output we get is a dendrogram. If we have a really big data set and we try to do agglomerative clustering on it and generate this dendrogram, what would happen?
Could you repeat that again? Sorry. I was-
It would take a long time.
It would take a very long time. You would have a very tall dendrogram. The question was, if you had a really large data set and you tried to do agglomerative clustering on it and get a dendrogram and then try to split it and figure out what's the best cluster, why would that be bad? And it's because it would take a really long time. You start off with each point being its own individual cluster, and that takes way too long. So if you don't have a big data set, agglomerative clustering is great because you don't have to decide sort of how many clusters you want. It sort of gives you all the values of all the clusters you could possibly do. And then from there you get to choose. If you have a very big data set, the first step is to inspect it visually. Are these clusters very well defined? Can we see them based on like location or density? Can we see that they're very obvious clusters? If we can't, then you want to use a Gaussian mixture model. Why would you want to? If your clusters are blending together, why would you want to use a Gaussian mixture model?
Differentiate them based on like the probability.
Yeah,
Yeah, so you can have overlapping, you can have mixed data. And with k-means, it's always one or the other, so it's good for clear borders, but not for messier data.
exactly. If you have overlap between your cluster, you don't have a clear thing. Using a generative model, using a model like a Gaussian mixture model will allow for you to look at probabilities specifically within them. And at the overlapping points, it'll be better. You will have a better look at your clusters than with k-means. So let's say you do have very well separated clusters. Then you can just look at how accurate you want your clusters to be. If you really want high precision, you want to use a Gaussian mixture model because of the fact that it gives you a probability distribution. Having a probability distribution for your data is very powerful. You can do a lot with that. Because if you don't, you can always use k-means. So that is the idea of clustering. Okay, does anyone have any questions on this graph? On when to use each? Does anyone have any questions on k-means, agglomerative, or Gaussian mixture models? Yeah.
Which one's agglomerative?
Agglomerative is the one where you sort of have everyone be an individual cluster, and then at each step of the way, you put together the two ones that are closest to each other. Keep making them closer and closer until you reach this top point over here, where everything is just one cluster. And then you go through this dendrogram, and you're looking at it, you're like, which one is the best value? Which is the best split of my data? Which one most accurately shows it? And you can choose how you want to split it. You can choose over here where P and Q are together. Or last time we said these are A and B, but A and B are together, R and S are separate, and T and U are together. That's what agglomerative is. Any other questions? No? Okay. If not, that's it. That's what clustering is.
Oh, hey.